Hi everyone. So today we'll continue on IP4. It's a prerequisite for this class, DCC, Data Computer Communications, but I know few did not talk about it. And before we start talking about IP version 6 and mobile IP version 6, I thought that we should explain IP4 quickly to see why it's not going to work for IoT, right? That's how IP4 now is running all over, but we need to go to IP6 and for mobile IP6, especially that most of the IoT is supposed to be mobile. So it's good to know the basics, the foundation for all of that. So last time we started talking about IP addresses. We said it's how many bits? It's 32 bits. Right. This is which one? IP version 4, right? We can soon talk about the 6, which is bits. IP version, this is 4, this is version 6, right? And we'll start talking about the address. We said there is two sections. There is an IP address, right? Okay. There is a network address, and there is host address, right? And we said for the IP address, we could look at it, the old system and the new system. The old system is a class 4, okay? The new system is a class less, okay? And the class 4 is divided to how many classes? 5 classes. A, B, C, D, E. These are used. This is for broadcast. This is reserved. Okay. Right. So explain last time how we can know the class. Okay. So how you know the class?
By looking the first bits of the
first bits. So if it starts with 1, then A, right? Okay. Then 1, then so 1, 1, 0, then 1, 1, okay, right? Remember? All right. And the best thing we said is to memorize the range for the first 8 bits from 0 to 127 plus 8, 128 to 191 is a class B, 192 to 234, I think it will be a class. Just, that's what we were talking about last time, right? So explained a lot. Let me do it this way. It's easier to do it this way. Easier for me this way. Sorry, I didn't want to do it the touch side. We're going to go fast or please. Alright, so we spoke about IP4, alright? We spoke about how it's a 32-bit, it's divided in 4 sections, each section 8 bits, and how can we write the IP address, and how we convert from binary to decimal, right? We spoke about these operations because we need them for the net mask, and how to find about the So finish the class full. So for example here, this is the network ID, this is the host ID. Alright? So in the network ID is in bits, the host ID will be 32 minus n, the remainder, right? Then we spoke, I think, last time about super netting and subnetting, how to make the network bigger and smaller. Alright, so here, cover all of that, just let me remember where we start. Okay, so here, what we are doing here, subnetting, right? Subnetting, right? We make the network address bigger. Make the network address bigger. And we spoke about the purposes for that. So let's talk a little bit about classless. So last time we spoke about classful, all right? Addresses. Today we'll talk about the classless. And again, I'm going to go fast because I am under assumption you know all this stuff. You should know this stuff before you take this class. Okay? So subnetting and supernetting is in a classful addressing did not really solve the address depletion problem. We didn't have a lot of IP addresses because there is some you know, for example, any address is ends with zeros, it cannot be used. Any address ends with ones cannot be used. So with the growth of the internet, it was clear that a larger address space was needed as a long-term solution. Although the long-range solution has already been devised, which is called IP6, a short-term solution was also devised to use the same address space but to change the distribution of addresses to provide a fair share to each organization. The short-term solution still uses IP4 addresses. Needless to say that IP address is still the mostly used. Alright? I started teaching IP6 maybe 20 years ago. So every year we thought that would be the end of IP4. IP4 is still existing. There are so many reasons for that. You could Google it to know why we have IP4, but all valid reasons. Eventually with IoT, with so many IP addresses, not only the need of the IP addresses, the need of many other things. You know, the need for things support mobility nicely, multimedia. Remember in 20, 30 years ago, how much videos there, how much multimedia there? Not existing, right? Nowadays, for example, think about yourself. 10 years ago, when you used text, what was most of your texts or emails? Text content. Nowadays, video. Even if you want to tell somebody good morning, you don't write good morning. What do you do? Good morning, you send it. Alright? So it's like it's becoming all of that. So we're trying here to have a variable length of blocks, two-level addressing, block allocation, and subnet. So what you'll have in here, you'll have variable length of blocks in a classless address. So you have block 1, block 2, block I until the last block M. So that's the address space how it's divided. So in a classless addressing, the prefix defines the network and the suffix defines the host. Same as a classful. What is the difference? The difference, they are fixed. So for the class A, it's 8 and 24. Class B, 16 and 16. Class C, 24 and 8, fixed. In here, it will be flexible. Okay, the network address and the host address. Alright? So you can have a prefix, not necessarily to be 16 for class B. It could be 15. It could be 12. It could be 10. It could be 21. Alright? And the rest will be in the host address. Alright? So we don't deal with the classes here anymore. Okay, it's a classes. So the prefix length is classless addressing can be from 1 to 32. From 1 to 32. So for example, what is the prefix length and suffix length if the whole internet considered as one single network? So what would be the prefix? Okay, so if this in this case, the prefix will be 0 and the host will be 32 bits. So how many IP addresses will have? 2 to power 32, which is about 4.25 billion. If you presume that we have only one network, okay, we don't. This is like, so what is the prefix length and suffix length if the internet is divided into blocks and each block has one single address? So what is the size of the prefix? That's another extreme. 32. Okay? And each network has one address, one IP address. So in this case, the prefix length of each block is 32 and the suffix length is 0. All 32 bits are needed to define 2 to 32 whatever blocks. Alright. The number of addresses in a block is inversely related to the value of the prefix length, n. Right? A small n means a large block. A small n, that's what inversion means. Small n it will mean a large block of IPs, block of IPs. A large N means a small I. So what will happen in here, that's how we write the IP addresses. We really saw that. Byte 1, byte 2, byte 3, byte, and in here what we have slash N. So the new system has slash N. What's N means? What N means?
The last.
What?
Last.
Stand up and speak up.
The last.
Last bit's where?
The 32, 32nd.
It's the number of bits of the host or of the network?
Number of bits of the rows.
Of the network. Thank you. Of the network. All right. The number of bits of the host this will be n or 32 minus n. All right. All right. So our class is addressing. We need to know one of the addresses in the block and the prefix length to define the block. If you need to define the block, that's all you need to know. You need to know the okay, so let's get a lot of example here, for example. In a classless addressing, an address can per say define the block the address belongs to. For example, the address 230.824. What is this? I mean, if it's a classful IP address, what class is this? Class C, right? All right. What is the size of n? N.
8 bits.
Huh?
8 bits.
N 8 bits?
8 bits.
No. C. What's the class? What's the size of n? 24. Okay. It will be 24, right? If it's right, right? So that's what we have in here. Guys, did you go over the presentation last week? No. So this is n, and this is 32 minus n. So in class C, this is how much? 8, and this is 24. That's in a classful. All right. So, but in a classless, okay, it's can belong to many blocks. Some of them are shown below. So in a classless, we don't talk about class A, B, C anymore. Okay, this could belong to multiple blocks. All right. So for example, if the prefix is 16, okay, not 8, 16, then the block is, the network address will be 238.00, right? Because of 16, 255, not 255.0.0, right? You end it with this and with the address, and it will belong to that block, right? Right? If it's 20, okay, then the block belongs to 238.16, right? Because it's not 16, and that will be the range there. If it's 27, okay, it will belong, the network address will be here. This will be the network address. Okay, and so on and so forth, right? So basically, we don't use classes now. The network size and network bits are different, right? How can you know the network size, the network size from the host side? By doing the net mask, net mask. So basically, how you calculate the net mask? If it's, for example, okay, let's talk 20, right? Let's talk 20. So 20 will be 1, 2, 3, 4. Okay. 6, 7, 8. What is this? 255. 1, 2, 3, 4, 5, 6, 7, 8. 255. Now, how many remains? 16 plus 16. 8 plus 8, 16. How many remains? 4. So this would be 1, 1, 1, 1, 0, 0, 0, 0. The last one would be 0, 0, 0, 0. Right? So let's calculate the network mask. How much is the network mask? 128 plus 64 plus 32 plus how much? Plus 16. How much is that? 400.
232. 232.
232? 242. So it would be 242 and 0. Huh? Oh, this is 240. Sorry. 240. Right? So that's the network mask. That's the network mask, right? So where is the side? Where is the side of the network address in here? And this is the side of the host address. All right. All right. So we started from a standard that the network side could be 8, 16, 24 plus A, B, C, right? The A, B, C, right? All right. Now we are removing these boundaries. We are removing this boundaries. All right. Clear? All right. So following addresses are defined using slash notation. So the address is address in here. This address, okay. The address in here, you see it? So from here, what is the network mask? So 8 means what? N. So what's the network mask in here? 250, 5.0.0.0. Right? Alright? So the network mask is 255.0.0. The mask has 8 ones and 24 zeros. The prefix length is 8. The suffix length is 25. Let's do this. What is the network mask?
16.
16. That means it's 255.0.0. All right. So this kind of class A, class B. Above the unit 27. So what is the network mask?
255.255.1111
Exactly. So in here, so 255 dot 255 dot 255. So how many ones in here?
8 1.
24. 8 plus 8 plus 8, 24. How many remaining?
2 more.
2.
Sorry.
3 more. So it will be 1 1 1 0 0 0 5 6 7 8.
Yeah.
So if you convert this, it will become how much? It will become 224. That's a network mask. Right? That's a network mask. Alright? So I think the idea is clear that we don't have, so you have from this, so the way you write the IP address, it's not only 4 parts, it's 5 parts. 4 parts slash a number. That number will tell you the number of ones in the network mask, starting from left to right. From this number, what we can calculate?
The subnet.
The subnet mask. All right. From the subnet mask, what we can calculate? The network address. Because how you calculate the network address? You're adding the IP address with
The subnet.
the subnet mask. Simple. All right. The process is simple, right? All right. So that's what we do in here. So look in here at this in here address. So this is what the address, and this is what the subnet mask. We just calculated. Remember the 3 ones in here?
Yes.
You added what we get in here, the first address. You get the first address. So the value of n is 27. The network mask has 27 ones, left to right, right? And the rest are zeros. So this will be the network mask. From the number, from the 27, you can calculate the subnet mask. So we use AND operation to find network address. The network address. Okay, the first address, you add it together. Okay, you get the first address of the network address. Alright. Why is that? It's very important to know the network address. Routing, for routing. All right. So to find the last address, we first find the complement of the network mask. What's a complement?
Zeros to one, one,
Zero, exactly. And then what you do, OR. Then what you get, the last address. So now you know the block starts from where and ends where. What is a block of IPs? IPs, sequence of IPs, starting from the first one and end with the last one. So that's the way you calculate the first IP address in a block and calculate the last IP in the block. Okay? So one of the addresses in the block is this one. So this is one of the addresses you are given. Okay? Somebody told you one of the IP addresses in the block is this. So remember that we are using classless. If it's a classful, 17 means class what? 8. You don't use it, okay? So the first thing we look at what? 24.
24.
So how many ones in the subnet mask? 24. Okay? So it means 8 plus 8 plus 8. Right? 8 plus 8, 16 plus 8, 24. So how many bits for the host ID? Only 8, right? So this is easy one. Okay, but the way to do it, the network address mask is 255 to 5550. So from this number, we can calculate the network mask. Okay, the number of addresses in the network is 2 to the power 8 to 56. It's exactly like which class? C. But again, we're not talking about class C here, right? Okay, it looks like class C, but it's not like C. To find the first address, we use the shortcut method discussed earlier in the chapter. The first address is, okay, so this is the address, this is the network mask. Okay, what you have to do? ANDing. So the first address would be 60, 17, 63, 110, 0. So very easy. You don't even do this because you could treat it as a class full. Okay? Okay, so to find the last address, what you do, you have the address, okay, and you have the complement network, and then you OR them, you're gonna get the last address. You're gonna get that last address. Okay? Very simple procedure, okay? Look at another example. One of the addresses in the block is this. So what's the first thing we look at?
Number 20.
20. It tells you number of ones in the subnet mask. You can calculate the subnet mask. What's the subnet mask? 255 and 250 plus 0. So how can you know the number? It's like 2 to the power 32 minus 20. That's the number of IP addresses. 4K, 4,000 IP addresses. Alright, to find the first address, very simple. You have the address, you add it with the network mask, which you calculated in here, will give you the first address. To calculate the last address, we do the complement. Okay, so what's the complement for 255?
0.
0. What's the complement for 255? 0. What's the complement to 240? 15. Alright? You do the OR operation, you're going to get the last address. Right? So now, in other words, okay, in a classful network, how many blocks we have? Kind of 3 blocks, right? C block, A block, B block, right? In here we have a limited number of blocks. So we have to, when we are given a block, you'll be able from the slash number calculate the network mask. From the network mask, you could, with AND operation, you could calculate the first address, and you complement the network net mask. You OR it with the IP address, you could know the last address, you know the size of the block. Simple, right? Simple, right? So, an ISP, this is an example. An ISP has requested a block of 1,000 addresses. Internet service provider, they need a block of 1,000 addresses, right? Okay, the following block is generated. So since 1,000 is not the power of 2, so you have to go a little bit higher to make the power of 2, which is 1K, 124, right? Addresses are granted, which is 2 to power 10. 2 to power 10, right? The prefix length for the block is calculated. How can you calculate the prefix? N, how much total in N? 10 is going to the host. How many remaining for the network address? 32, okay? Minus log 2, 24, 22. Okay, 22. So the beginning address is chosen as, you chose the beginning address, 18, 14, 20, which is divided by 24. The granted block is, this is, we started from this first address. 22 is the number of ones for that. And the first address, this, you know how to calculate it, and the last address is this, you know how to calculate it. Right? Very simple, right? So, prefix length in the class 4, you have A, B, C, slash A, slash 16, and slash 4, right? That's what we have, right? So, assume an organization has given a class a block 7300. So that's a block. 73 is supposed to be class A, right? Okay, in the past. If the block is not revoked by authority, the classless architecture assumes that the organization has 73.0.00/8, right? Which is a class A. So the restrictions applied in allocating addresses for a subnetwork are parallel to the ones used to allocate addresses in the network. Anyway, so let's take this example quickly. The organization is granted the block. So some organization, your organization, granted this block. So from 26 you could calculate the subnet mask. You could calculate the first address, you could calculate the last address, and you could calculate the size of the block you are given, right? The organization needs 4 subnetworks, each with an equal number of hosts. So we don't need one network, we need 4. And all of them have the same number of hosts. 32, for example, 4 subnetworks of 32 IPs, or 8 IPs, or 64 IPs, or 30 IPs, whatever it is, right? Design the subnetwork and find a solution. So, the number of addresses for the whole network can be found 2 to the power 3 to 32 minus 26, which would be 64. If I need to create 4 subnetworks, how many IPs in each subnetwork should be? 8, right? 16, I'm sorry. 16, because 64 divided by 4 give you 16. So, network 1, network 2, network 3, network 4, each one will have how many IPs? 16 IPs, right? So the first address in the network is this. How I calculate this? And with the subnet mask. How I know the subnet mask? Calculating for the 26. Alright? Alright. And the last address is this. How can I calculate it? Or with the complement of the subnet mask. Easy so far, right? Now, to design the network, we grant 16 addresses for each subnetwork to meet the first requirement. 64 over 16 is a power of 2, which is good. Those are the power of 2. So the subnetwork mask for each subnetwork is like this. So network 1, network 2, network 3, network 4, all of them will be equal and equal 16 IP addresses, right? This is the size of a block, which equals to n. How much is n? 26 minus log 2 for 64 over 16, which is 26 plus log 2 for 28. So each subnetwork now has it will be what? It will be 28/28. Clear? Alright? /28. Okay? And this network, so the network will be, okay, it's 130.34, I'm putting in here, .12.64/28. This will give you how many IP addresses?
2 raised to 32 minus
16, right? And this will give you 64 IPs, right? Right? So we have one block, we divided in how many blocks? 4 blocks. 4 blocks. Right? So, alright, we grant 16 addresses to each subnet starting from first available address. Figure 530 shows a sub-block for, okay, that's what it is. So initially, I have this whole block. How many IPs? 64 IPs. Now divided in 4. Alright? So the first one has 16 addresses, 10 and 28, 10 and 28, 28, 20. Alright? So it starts from the first IP addresses, and this will be the last IP address we have calculated, right? And then, okay, so you take 16, then the following 16, following 16, following 16. So this will range from where? 130, 34, that's 12, that's 64, until 130, that's 34, that's 12, to 79. And this will start from 80 until 95. And this from 96 until 111, right? And this ends with 117. Alright? So if you are a network engineer, okay, you work for an organization, you will play all these games. All these games, subnetting, supernetting, okay, dividing. And remember that all money, I mean, you get these IP addresses, you pay for them, right? So it's like thousands of dollars, tens of hundreds of dollars in organization like you need to get these IP addresses. Alright? So you have to be very wise how to use these IP addresses. I'll give you an example, okay? Let's say that you have 4 building in UB, right? Engineering Tech, Dana Hall, Carson, Manpower, right? The easiest thing to say, let me get 4 C classes. Each one have 1 C class, 256 IP addresses. But we all know that, for example, Manville Hall has only 50 computers. So what you did? Waste a lot of IP addresses. So the better thing for you to get the whole block and do subnetting according to what you need. You don't want to waste the IP addresses, right? So a lot of design issue in here, okay, and this is very important when you're involving routing. I mean, until now we're talking about IP address. So how are you going to configure your routers? Because routers, what does it do? Connects LANs. Connects LANs, does routing. Okay? So an organization is granted a block of addresses with the beginning address. This is the beginning address. The organization needs to have 3 sub-blocks of addresses to use in the 3 subnets as shown below. That's what I was talking about. So not equal. So this is that's what they are granted. Right? They need one network has 120, 160, 110. It's a tougher problem. The previous one in here, they are equal, right? In here, they are different sizes, right? So how you start again? So how many total? You are given this block. How many total IPs you have? 2 to the power 8, right? Which is 256. So 256, you get 120, 60, 10. If you add them up, let's add them up. 120 plus 60? 180 plus 10? 190, okay? So of course, whatever division we have has to be power of 2. So for this network, you cannot give them 120, you have to give them what? 128. In here, 64. In here, 60. Alright? If you add them up, it will come to 56. Right? So the first address, you know how to calculate the first address, right?
Yeah.
Okay? You calculate the match, you end. The last address, you know how to calculate that, right? So the number of addresses in the first sub-block is not power of 2. We allocate 120. You understand? I already mentioned that, right? Okay? Alright, so you allocate 128 address. The subnet mask is 25. Not 24, 25. The second one and the last one. Anyways. So the number of addresses in the second sub-block is not about the same thing. The same thing in the third one. Okay. If we add all of them, it becomes that, okay, which means 48 addresses are left. Okay, there is a way to 48 addresses. Okay. Anyways, so that's how you'll do it. All right. Again. 128, 64, 16, and this is the 48 and used. So the idea of using a class list is to reduce the waste. However, it's impossible to reduce it to, not impossible, I mean, in many cases you cannot reduce it to 0. All right? But can you imagine if you, for example, you get a bigger class and you cannot utilize it in the right way. So I think I covered the idea. You could go over that by yourself in here. So here, for example, okay, here, for example, this is an network which is 70 and 28, all right, connected through our router, and that becomes a WAN to another subnet, to another subnet. So all the addresses are derived from the network. You take a look at that. I'm just giving you the basic ideas. Okay. There is always special addresses. There is always special addresses. So the class for addresses, some addresses were reserved for special purposes. The class list addressing scheme inherits some of these special addresses. Okay, so there is special class. So for example, okay, all zeros. Okay, all zeros. Okay, it means the network address. It's the whole network. Okay, destination page. So the address and all right. So and you know what's DHCP server? We explained what is DHCP server, right? Okay. So destination is 255. 255 means what? Broadcast. When you send a message with this address, that means it's a broadcast. Right? Because when you send a packet, there's a source address and there is a destination address. If your destination address is all ones, that means you're sending where? Or all zeros, I'm sorry, you're sending where? It's a broadcast. Example, like for example, in DHCP server. The DHCP server, you know what planning cost, allocation protocol. Alright, which is last night. There is also limited broadcast address. So, for example, in this network, we have. So, if you have, for example, destination IP address 255, 255, that's a broadcast. Broadcast means the message will go to all the nodes in the network, all of the network. There is always unicast, which is the message going to a certain destination. There is multicast to a group of hosts, and there is a broadcast to the whole network. Now, some of the functions of the routers, not to allow all the broadcasts to move through. Otherwise, there is so many broadcasts in the network that would cause a lot of problems. So, right? So example of loopback, all of you have used, all you programmers, so I'm sure you always tried, for example, ping 127.0.0.1. What is this? Address loopback, that you're pinging yourself, right? It's a loop called loopback address. All of us know this address, right? All right, but even if you use like chain one, the same loopback. So the whole class 127 is special. It's called loopback. So when you say, for example, that the destination is 127.x.y.0, any number, that's a loopback. So it's like you're sending the packet to where? To yourself. So why we use it many times? Troubleshooting for connectivity. So it goes out the message, and where's the destination? It's going to come to you. It goes to the router, it will come back to you. Loopback, right? All right. So addresses for private networks. So this block, okay, 10.0.0/A. The number of addresses. This is the block. Okay. and this is here that I'm blocked, there's another block number. So anyways, so it's very easy for us now to calculate how we calculate that number of addresses in a certain block. You know how to do it, right? Right? Example of direct broadcast. Direct broadcast. So here, for example, this is the whole network here, 21.45.71.0.24. So it's kind of class C, right? So same network, okay. And here, so if you have you have the prefix then, the network address, and in the suffix you have all ones. Okay, that's what we call it, direct broadcast. So if the destination address, if you send a message and destination address is the network address plus all ones for the host, right? That we call it limited broadcast. It will broadcast in the local network. It does not go beyond routers. Okay? So that's another special IP address. Another special IP address. NAT. You know what's NAT? Network address resolution. Okay, transmission. All right. So in NAT, the distribution of the address provider has created a new problem, which is there is no IP addresses. Right. So to save IP addresses, let's say that in your home, for example, okay, you are a student who, like your teacher, you cannot afford to buy, IP addresses. But you have you do a lot of research at your home, and let's say that you have 8 computers. Computer 1, computer 2, 3, 4 computers, right? Right? But you can afford to buy one static IP address for your network, which is like $100 a month or whatever, right? So what you have, one IP address, for example, 192.80.90.10, right? All right. So that would be your IP address. In here, what you give dummy IP addresses. Okay. So this you create a NAT server. You give it that address, and in here you could create dummy IP addresses. So for example, 200.0.0.2, and this one 200.0.0.3, 200.0.0.4, 200.0.0.5. Is there a problem? That all of these are connected to hub. This is a hub. Alright? So when you configure any computer, remember what you give. I'm sure you have, and most of you use DHCP. If you are configuring a static, there's 3 numbers you have to give. Can you remember them, what they are? The IP address?
The MAC address.
No. You didn't give the MAC address. MAC address is really great. The subnet mask? Mask. And the gateway. So the gateway, that is the address of the router. What does it mean, the gateway? Okay, it means that if you are communicating within the network, okay, you don't need a gateway. But if you need to go to the external world, where do you have to go? Through a gateway. All right? If we are communicating among ourselves in this class, we could communicate directly, right? But if you need to communicate with a professor in another classroom, we have to go through this gateway. Right? Right? It's a gateway, right? So that's what it is. So when these computers, 100, 200, 4, like my example, communicate internally, okay, there's no problem to communicate. And all of them, when they need to communicate with the whole outside, okay, they have to replace the source address to the real address, okay, in sending the packet when they communicate outside. So that's what we call it, network address translation. So instead of using the local address in here, when you communicate with the external world, we use one IP address as a messenger. Exactly what it is. So this is all of us having IP address. This guy is a real IP address. You are including me fake IP addresses, right? He's an IP address. So when I need to communicate with you, we don't need him. Okay? He stays. Okay? We need to communicate with you. I don't need him. Now, when we need to communicate with the other professor, okay? So we send the message to him because he's the only one, because he's a real IP address. That principal can go deliver the message. So if I need to send it to the professor in the room, okay, I'll create the message and give it to him. He will replace my name with his name. He becomes the address, and he will go deliver the message. Right? The same thing. When any message comes from there, the only message comes from the whole world. It can go to where? To him. And him knows where to deliver it internal. What do you call this? Network address translation. Network address translation. What is the purpose of this? To save IP addresses. Right? So a network of 100 computers, you could use one public IP address. One public IP address. Right? Instead of paying 100 times 100, how much? $10,000, you pay $100. Is there a problem with this? Is there a problem with this system? There's no problem? It's good? All good? Sure? It's not slow, it's not, you never feel busy. You are good. Yeah. It could degrade the performance of them. Right? But again, it's a solution. Right? Where is it good? When is it good? When is it good in your opinion? You're an engineer, I think, right? When is it good? Exactly. When the traffic outside is low. Because when the traffic outside is low, most of that work, the communication side. But once in a while, you need to have the external communication and all that. So that's what is NAT. That is NAT. All right. Do you think it will be useful for IoT? Maybe, right? Maybe. Okay, so that's what I explained, right? So you have local network. These are not real IP addresses. All of them not. Okay. This is the only real IP address that is routable. So whenever this computer needs to communicate with the internet anywhere, it has to replace its address with real address, with the real address, and it becomes communication, right? So you see in here, this is the address. 172.18.3.1, all right? And when it goes out, it will be replaced with a different IP address, which is the real routable IP address. All the data gonna come through this IP address, but the NAT server will be able to replace it with the real internal address. So my question to you, IoT useful? Is this useful for IoT? Yes. Let's say that you have like 100 IP devices at your house. Something to monitor the refrigerator, something to monitor your doors, windows, IoT. Let's say you have a smart house. Smart house. Can you afford to have 100 IP addresses? $10,000? Right? Can you? Maybe you can. You don't believe me. I mean, you look different. So how about you? Can you? So you think this would be a useful solution? Huh? Especially that usually the IT devices, by definition, is supposed to send very low data. They don't send a lot of data. And there is other things we do, aggregation. So usually try to, do some work with the data before it's transmitted and all that. Maybe, right? But definitely, when we're talking about IP4, you know how does IP4 work? We're going to talk about IP4. We know how big, how sluggish it is. Okay? You know that it might not be the right solution for many applications, right? That's why we're going to go to IP6, okay? And we need to improve. IP6 work by itself, there's something called mobile IP, okay? Mobile, okay? So we're going to talk about later about mobile IP6. IP running and why mobile IP is involved? Because, this now, it has an IP address, right? Right? and connects to the access point in here. So usually when you are part of the network, you are physical there. But this is a mobile. It will be in a train in 5 minutes. So which network you connect to? So the current IP does not work. We have to have a different system called mobile IP, right? Anybody took wireless communication with me? We spoke about mobile IP at that time. All right. So that's what you have in translation. There is a table in that server that does the translation. Okay, translate the source and all of that. So, all right. I don't think I have time to talk about delivery and forwarding of IP packets. So maybe we'll keep it for next time, next class, or Thursday. Thank you so much.